Okay, so in this experiment, we're going to be playing around with the pulse width, and we're going to see how that affects the speed of the wave. So we're going to start, we're going to go off back to the simulator, and we're going to restart that. So that's in the upper left-hand corner up here. Click Restart. And then, if your timer's going, you want to reset your timer, so you want that to read 0. Okay. And then the next thing that it tells us to do is to press the green button to create a wave or a pulse. So here comes a wave. You know what? That wasn't very good. Let's restart that. So right away we want to hit start after we send the pulse. Okay, and then what you're going to do is find the time it takes for that wave to get all the way to the other end. So you're going to need to go into the actual PhET simulator to do that. I'm not going to show you what it is this time. Then you're going to change the pulse width. You're going to restart. Then you're going to change the pulse width to 0.95. And you're going to run the experiment again. So we'll go. Right? And you're going to let it go all the way down to the end and try to determine how long it takes that wave to get to the end. Okay, and then answer the question as the pulse width increases. So as it goes up, what do you notice about the wave speed? Is it slower, faster, or about the same? And then there's this question: what's the difference between pulse width and wavelength? Wavelength was a word that we learned yesterday, right? Remember, that's the distance from one crest to another crest, or the top to another top, or it could be from the bottom to a bottom, right? Remember, the bottoms are called troughs. Well, in this experiment, we were changing pulse width. What's the difference between pulse width and wavelength? Well, pulse width is how long it takes this little piston here to come up and then come down. So let's restart this and see if we can time that. So time it takes it to go all the way up and then all the way down. Here we go. It's all the way up, all the way down. Looks to me like that was 0.76. And of course, my reaction time is going to be a little bit slow because I got to go from the pulse to over here. But the pulse width, it should have come out to be 0.95. The pulse width is just how much time it takes it to go all the way up and then all the way down. Okay, so then how does that relate to wavelength? Remember that wavelength is just the distance from the bottom to the bottom of the wave, or the top to the top. So let's see what that looks like on the slideshow here. So here we've got a wave that I just took a screenshot of. We can see that the pulse width was 0.35 seconds. So it took 0.35 seconds for the piston to go all the way up and then all the way down. Okay, so then let's measure what the wavelength is. We should see that the wavelength is the distance from the bottom to the bottom here. So this point looks to me like it's at about 1.5 centimeters. And this point right here looks to me like it's at about 2.15 centimeters. And then we calculate what the distance from one point is to the other by subtracting. So if we just take 2.15 minus 1.5, we get 0.65 centimeters. So that's how long this is, 0.65. So that's the wavelength. The wavelength is 0.65 centimeters. And remember that the pulse width, that's just how long it took to make the pulse, to make the wave that took 0.35 seconds. Okay, now let's compare that to the longer pulse width. So this one was 0.95 seconds, so almost 1 full second it takes the piston here to make the wave, to go up and then come down. And so then let's measure what the wavelength is here. This is 0.9 centimeters. This one is at 2.4 centimeters. Again, we're going to get the wavelength by subtracting. So we're going to go 2.4 minus 0.9. That's going to get us to 1.5 centimeters. That's the distance across the top here. So let's compare those two. For the short wave, it was a pulse width of 0.53 seconds and 0.65 centimeters for the distance. Now watch, both those values are going to increase. When you increase the pulse width, 0.95 seconds, the wavelength also increased. So basically, the longer the piston goes to make the wave, the longer the wave is, if that makes sense. And so, what does that mean? Pulse width and wavelength are positively correlated. As the pulse width increases, the wavelength also increases. So what does that mean in terms of the wave speed? Well, we said that as the pulse width increases, the wave speed pretty much stayed the same, right? That should have been what you got for these two, is about the same time. Well, that means that as the wavelength increases, the wave speed is also going to stay the same. The wavelength and the pulse width, those don't really affect the wave speed.